Assalamualaikum warahmatullahi wabarakatuh, and a very good morning. So, can you guys hear me? Please respond.
Yes, doctor.
Okay, very good. Okay, so today this week is actually already week 6. So we are going to cover a new chapter, but still related to a Z transform. Okay, and as a reminder, so this week also we have a test one on at our class Thursday. Okay, so we're not going to have any class, so we will do the test one at class time on Thursday. Okay, so all right, so our new topic for this week, so it is what we call an LTI system function. So this is a new term, right? So we have what we call it. What is a system function? So we will look at what is this actually. Actually, we already look into this thing, but we didn't call it as a system function. Okay, so what is actually system function? System function is actually HZ. So we have seen what is a HZ. So HZ is a Z transform of a time domain signal, okay, of an impulse response. If you have an impulse response, do Z transform, so you will get HZ. So actually that HZ has a name. So it's called a system function. Okay, but let's see some recap so that we know what actually we are trying to cover today. So this is from our previous several weeks ago. So we have covered about LTI systems. Actually, we start doing this on week 3. Okay, so week 3 we start covering LTI system. So what is the LTI system? LTI system is a linear and time invariant system. Okay, so and here we are referring to a discrete time system. Okay, so because in a continuous time system, you also have LTI system, but this one we are referring to a discrete time system. All right, and if you realize from e-learning, so actually we have several revision video. So those things. So this is actually this week. So there's a revision on RC circuit. So the RC low pass filter circuit. Okay, and then something on memory. So these are actually a continuous time system. These are actually using LTI system also, okay, but on continuous time. So actually we need to understand what are these things. If you did watch this video, so you will see what will be the difference today. Okay, so we're going to cover actually the same thing, but in terms of a discrete time version. Okay, so okay, let's see what is the LTI system. So this is the LTI system last time. So let's play this thing. So we have represented. It can be represented by difference equation. And so what is a difference equation? Again, this is one term which is very, very important, because LTI system, when you see one equation such this, so this is what we call difference equation. And if it is called difference equation, then actually this is a discrete time LTI system. Okay, so if it is a continuous time system, LTI system, so we call it differential equation. So there's a little bit different here. So one is a difference, the previous from your courses, from your previous courses. So we call it differential. Okay, so that's the difference. Okay, so yeah, so we have this. So we have 3 operations. So we have delay. So we have a summation, those are summation, and then we have a weight multiplication, and then the weights are actually the filter. We call it there's 2 types. So one is whatever the value multiplied to the output sequence. So these are output sequence. So we call it coefficient A, right? And those which is multiplied to the input sequence, so we call it coefficient B, right? And we have seen that we have 2 types of impulse response. So this is that's why if you look at this thing, let's go back a bit. So this is what we call a difference equation, and then we have a coefficient. So there's a coefficient A, coefficient B. So when implementing this system, LTI system, so how do we implement discrete time system? Of course, using discrete digital system. Okay. So how do you implement a continuous system? How do you implement that? So discrete system, so we are using a digital system like a processor, microprocessor, the one that you have learned. Okay, so maybe we have VLSI design, those kind of things. So, but if you are designing, let's say, a continuous time system, so the analog, so how do you design it? How do you implement it? How do you make things like, let's say, LTI system, a filter, a continuous time filter? So how do you make it into a product? So how you do it? Anyone remember how you do that? Anyone, please? So because we have learned many times on a continuous time system. So how do you implement it? How do you implement it? No one wants to try? We just started, so hopefully everybody is still fresh.
Doctor, you mean that we write it in a form of sum?
Pardon again?
Write it like the same in the difference equation in form of a summation. So, for example, it's a sum. 1, 2, 3. It's a sum 2, k equal 2, and if I'm not mistaken, bkx n minus k.
That's the equation.
That's
Okay.
an equation. Okay.
That's the equation, right? Of course. What I mean here is for a discrete time system, discrete time. So how you going to implement it is actually either you implement it on a microprocessor. Okay, so that's one example. Or maybe you just design some gates. Okay, so how do you implement it on a microprocessor? So you write a coding. Okay, those things are discrete time. Those things are digital system. But how do you implement? How do you make a product with continuous time? The analog system. So you want to make a analog filter. So how do you implement it? How do you do it? So you've been through 3 years. Most of it are actually a continuous time system. So you should know. So can someone try? This is a very basic concept. So try it. So at least you will know now. Come on, if not, you're not going to continue. Try anything.
Digital to analog.
Digital to analog. So that's when you have a digital signal already in your microprocessor. Okay, microprocessor or your computer, and then you can convert that into a continuous time again. Okay, so but if originally you want to have a digital continuous time, let's say a low pass filter, but we want it to be continuous time, analog low pass filter. So how you do it?
RLC circuit?
ROC circuit?
RLC, I mean capacitor.
RLC circuit. Yes, that's true. Thank you. Okay.
Credit
So
to
we use RLC. We use op-amp, just since it's op-amp. Very good. Okay, so we design a circuit. So we take our R, C, L, and maybe most of the application is now using op-amp, right? So if you are, let's say, playing a guitar, and then you want to make a very unique sound, so you plug in into something like okay, you buy something, some device so that it can change the sound of your guitar. But the one that you buy is analog. So inside that device, so there should be RLC and op-amp, all of it. Okay, because those things are actually filtered. So you need those things: the resistor, the capacitor, the inductor, the op-amps. But for discrete time system, it doesn't need those things. Doesn't need those things. So what you need is a processor. Okay, so or maybe a gate system. Those kind of thing. Everything will be in digital, and everything must be now. Everything can be programmed. Everything can be programmed. Okay, so now we know that everything is supposed to be in your digital system, in your microprocessor. So what we do here is actually, if we have this system, so this is the equation. This is the equation, and we have a coefficient. So in a digital system, so this coefficient will be placed into memory, right? And this is fixed. If we look at this equation, that green and orange values are actually fixed. So these are fixed values. So that's why we call it coefficient, right? And a fixed value supposed to be placed into ROM. So you're going to save this into your ROM. Okay, and then when you want to implement the filtering, so this is actually implementing the filtering. So what will you do is, so you're going to the CPU, the processor. So we'll do the plus, we'll do the multiply. Okay, so that's the arithmetic operation. So multiply, plus, and what is this? So what is inside that bracket? So how we do that? Can someone guess or know the answer? So how we do this? This is quite clear. So this is multiply, right? So in our CPU, we can do multiply, no problem. And then we can do plus, no problem. This is everything very clear. Okay, but what is this? Because in discrete time system, so this is very important. So we have a delay. So we call this delay. So but how do you implement this? How do you do this in your digital system? How is it? So you have learned a microprocessor, right? You have learned the digital system. So you have learned about memory. And I have told you that this is, you're going to place this in your ROM. So do you know how we implement this? Okay, everyone is too slow. So this is, you place this on your RAM. Okay, because if you need yn minus 1, yn minus 2, so means that you need to place on your ROM, your RAM, 3 values. Okay, so this is the 3 values in your RAM. This is the 3 values in your ROM. 3 values again in your ROM. This is a 3 value in your RAM. So then do the multiplication and sum in your processor. Right? So can you guys imagine that? Because that's how digital system works, right? And actually those things have been covered in several courses last time. Okay, because we are going to be what we call actually those things is a low-level processing. Low-level processing. The lowest level processing is when you learn about electronic digital. So how to do the binary number, you have a gate and or those kind of thing. And because this is either a third year or fourth year, so actually we are doing a high level processing. Okay, so because we have all the data, so how are we going to process it in a digital version? Right? Okay, so hopefully slowly, if you don't understand what I explained, so watch back this video slowly try to understand it, because it is everything about electrical engineering. It's not just on this course. So we need to combine all your knowledge now so that we know what is actually we are learning. Okay. All right. So we have this, and we have seen this before. So impulse response. So we have two types. One is the FIR. Okay. This is coefficient, which is representing difference equation, and this difference equation can be converted into impulse response. Another term, difference equation, impulse response. What is the difference equation? A representation of LTI system according to input and outputs. And we will see the process of it. So what is the process? Multiplication, delay, and plus. Right, and LTI system can also be represented by impulse response. Right? So we denote it as a Hn. So just a vector. This is an equation. This is a vector. So, and then we already know that for FIR, our impulse response is actually equals to B. So this one, because actually for FIR, so we have the A. The A is actually equals to 1. This is for FIR. This one, oh, okay, already here. Right? So Hn is equals to B. The A is equals to 1. So that's why we only have a Yn. We doesn't have other output sequence. So we just have Yn. So, and we need this, And for Yn, you cannot have a multiplier other than 1, because we are trying to find what is the output. So we doesn't want to find a 2 times output or half of the output. So we want to have outputs. So that's why this value A equals to 1 for Yn is fixed. So you're not going to change this, because it's not reasonable, it's not logic to have 2 times outputs. Okay, so it's supposed to be just outputs, Yn. And last time we have seen that there is also IIR, infinite impulse response. Okay, so we have 2 types of impulse response. So very important for your test, because we have 2 things. One is the FIR, another one is the IIR. And for infinite impulse response, so we cannot do the conversion between difference equation and Hn straightforward. Okay, and this is from last time. So we have note that. So we need to use a Z transform. So we need to use Z transform. Okay, so if you are given Hn, if you want to get a difference equation for IIR, so we need to use Z transform. Or if we want to, if we have a difference equation and once we have impulse response, again, so we need to use that transform. Okay, the other way. Right, and but for implementation, whatever it is, when you want to implement it on your digital system, so actually this is the one that we applied. This is the one that we store in our ROM, and this is the one that we run on our processor. Okay, it's not the Hn, it's not the impulse response. So why do we need impulse response? For analysis. So this is for analysis, just to look at whether it is stable, causal, and several other things, but we're not going to cover it in this course. We just cover stability and causality check for Hn. Right? Last time, if you when you learn about control, basic control, so there's a very important things why you need to learn what is the impulse response, and the other one is a step response. And step response is very important for control. Okay, and of course in your control design, so you should have this difference equation also. But because you need to do a lot of analysis last time, so actually you are focusing on the step response, the impulse response. Okay, so there's a reason why we need to have this thing. And for this course, we just use it for stability and causality check. right? But of course, it's not the only option. It's not the only option to check stability and causality, because stability and causality, we have three options. One is this one, checking impulse response. The other one is checking the difference equation. The other one is checking the ROC. So three methods. Okay, so three methods. And today we're going to, in our first, this is our first session. So we're going to do this one. So we have done this because this is very straightforward. So, but we're going to do this. How to convert between impulse response and difference equation using Z transform. Okay. So this is where we will start on this topic, what we call a system function. Again, what is a system function? So it is also called transfer function, and it is a function in Z domain that relates the input signal xn with the output signal yn. Okay, so this is hz. Actually, hz is just you can convert this into inverse. So you do the inverse Z transform. So what you will get is impulse response. So system function is actually just Z transform of our impulse response. Okay. So then you have this one. So why this is very, why we are interested in this system function, hz? Because it gives us this relationship. So this is a yz divided by xz. So we can see the hz, we can see the yz, we can see the xz. Okay, but if we look at difference equation, so difference equation is also relating input and output. But then the hn is not here. So we can't see the impulse response. So what we see is just the coefficient. Okay, and coefficient is, we have two vector. It's not represented by one thing. So this is two items. Right? So that's why this is one of the things that if we want to do something in time domain, this is not really easy. But if we have it in Z domain, the relationship becomes easier to manipulate. Right? So where does this comes from? So actually this is from our last class. So we already know that. What is a yn? Yn is actually just a hn. Do convolution with our input xn. Okay, and we have seen one properties. Yn, if you do Z transform, so you'll get yz. And convolution in time domain is actually just multiplication in Z domain. So that is actually one properties of the Z transform. So you can try to check back our last class. So we have covered this at one point. So this is multiply. So then we have the hz. See, this is actually easier to be manipulated. Rearrange the equation compared to this one, because this is just a symbol of a convolution. So, and convolution is actually a sum of a weighted a sequence. Okay, so there's a lot of things in here. Everything becomes easy here, right? Simpler. Equation is simpler to be manipulated. So because hz holds the relationship between xn and yn, difference equation can be obtained from hz. Right? Because what is the similarity between hz of yz divided by xz and a difference equation? Because both is actually relating input and outputs. But this one is a relating input and output in time domain. So this one is a relating input and outputs in Z domain. Okay, so then we can actually use this to convert between impulse response and difference equation. Okay. Okay, so I'm just going to read this one because it is here. Difference equation is important in designing discrete system because it will be the latest product before the system can be implemented into hardware. For analog system, so we have discussed this, differential equation is obtained from Laplace transform. So we're not using a Z transform, we are using Laplace transform last time. Before it is used to construct the analog circuit, which is the RLC circuit, or using op-amp. Okay, so RLC circuits, we have seen RLC circuits even from year 1. Okay, let's see one example. So this is the first example. So what we have is a HZ. Okay, what we have is a HZ. And we want to get the difference equation. So what we do here is find difference equation. Difference equation. Okay. So of course, this example is not, we're not doing it from impulse response. So it's already halfway. So we already has the HZ. So then find difference equation. So HZ, so what is a HZ? HZ is just YZ divided by XZ. So from here that we know that actually then the upper part is actually YZ. The lower part is the XZ. Okay, because we always have this, when you have a HZ, so you should have your numerator and denominator. Okay, you have two things. Numerator is actually the YZ, the denominator is actually the XZ. Okay, then we do that, so replace that. So this is YZ, XZ, so replace this one. This is a HZ, replace it. So we have this thing. And then bring this thing, this part, the denominator, up. And then XZ, bring it up here. So this is what you get. So this is the YZ multiplied by those terms. And XZ multiplied by those terms. And expand that. So you have YZ plus 2Z minus 1 of YZ plus 0.5Z to the power of minus 2 YZ, and the rest for XZ. Okay, because this is just, we have one only. So this is XZ plus Z minus 1 XZ. And from here, so we can use a delay property of a Z transform. Okay, so let's see. I think I have okay, so this is from last time. So we have for Z transform, so we have two types of table. So one is a Z transform pair. Another one is this one, which is a Z transform properties. And one of it is this one, time shifting or delay. If you have Z to the power of minus delay of HZ, okay, so this is the HZ. So if this is H, then you'll have H here. But that ND becomes the delay in time domain. Okay, so if you have a Y here, then you will have Y here. If this is X, then this is X. So what is the difference? So this is using capital letter. This is using a small letter. Okay, because of that, so we know that this is a YZ. So no Z in front. YZ, this one, this YZ. So this YZ, there is nothing, no Z in front. But this YZ, so we have a 2Z minus 1. So we have a Z minus 1 here. So it means that our YN in this part will be delayed by 1 and multiplied by 2. Okay, so this is just multiplication. And this YZ, when converted it back, when do inverse Z transform, so we'll get YN, which is delayed by 2. And same thing goes to XZ. Okay, so this is where we have this thing. So the first one, there's no Z multiply to the Z, but this one, so we have a Z to the power of minus 1. And then this is to the power of minus 2. And this is the XN. And this is when your input XN is in Z domain is multiplied by Z to the power of minus 1. So this is our difference equation. And to make it more, make sense, so this is where normally what we do is we just put on the left side of the equation is YN alone. Okay, so that's how we write a normal equation. So on the left side of the equation, we just left the YN. So we bring the rest, this term and this term, to the right side of the equation. So we have yn equals to xn plus xn minus 1 minus 2 yn minus 1 minus 0.5 yn minus 2. Okay, so this is our difference equation, and we will use this in our digital system. Okay, so if you have if you need to code it, so you will write a program on how to do this. Okay, so because and there's several others digital design that we can do. Okay, but most of them can be programmed. So most of them can be programmed. Okay, so you need to know how to write a program. So you have learned programming even from year 1, so until year 4. Okay, so and maybe I think high possibility your final year project is actually doing programming also. Okay. Okay, let's move to another example. So this is example 2. Find difference equation for each z. So what we have here is a little bit different, the form. So this is in factorized form. So where we have a z to the power of minus 1 divided by 1 minus z to the power of minus 1, and then multiply by 1 minus 0.5 z to the power of minus 1. Okay. And this example is exactly why do we have this example? Why not just this one? This is not factorized. This is where you have all the z already expand. Okay, so you see that this is actually z to the power of 0, minus 1, minus 2, and the rest. So if we have it, but this one is in a factorized form. So why actually this is quite important is because when we do design later in week 12, 13, okay, so we will get this form. We will get this form. After you design, you will get this form. But you need the difference equation as your final product. Okay, so that's why this example is quite important. So what to do to get the difference equation if you have this kind of HZ? So you need to expand it. So you need to multiply it. 1 multiplied by 1, 1 multiplied by 0.5 z, or minus 1, and the rest, so that you will get this form. Right? So you should get this form. And then do this, then we know that so HZ is actually YZ over XZ. So this is our definition. So, and then bring this XZ and YZ to its site. So this is YZ, XZ, do that. And then you have a YZ, multiply 1 by 1, expand. And then we know that this is YZ. So do inverse, you will get YN. YZ, Z minus 1, do inverse, you will get YN minus 1. And this is just a multiplier. So, and the rest. So this is xn minus 1. So in this case, we doesn't have xn. So we doesn't have a current input. So we have a delayed input, so which is a xn minus 1. Right? So, and of course, if you want to make it a more normal, the way we write equation is actually this one is actually xn minus 1 plus 1.5 y and minus 1 minus 0.5 y and minus 2. Okay, so this is a more common way of writing equation rather than this one, but both are the same. Both are the same. Okay, no worry. So which one you want to write it, doesn't matter. And this is the third example. Okay, so now, so this is we are doing the things starting from impulse response. So what is the HN again? Because you guys need to be need to get used with these terms. Okay, difference equation, impulse response, FIR, IIR. Okay, those are 4 terms which is now very important. And we have another one today, which is a system function. Okay, 5 terms, 5 very, very important terms that we have learned. difference equation, impulse response, FIR, IIR, and then a system function. And one of the most important process is convolution. Okay, and we already know that convolution is in time domain, and in Z domain, convolution becomes just a multiplication. Okay, a simple multiplication. So, okay, so we have this. So we have seen this example a lot before. So then it will be easy to follow this example. So Hn equals to 0.5 n un. And straightforward, you just refer to the table. So let's see which table. Not this table. So you're going to refer to this table. Okay, so because what you have is 0.5 n un. This one. So actually it is this one. So it doesn't need to do any mathematical long solution. Just refer to this table. So ENUN is actually just equals to 1 over 1 minus EZ to the power of minus 1, where the ROC is a Z greater than E. Okay. So to make this complete, actually you should write the ROC is Z greater than 0.5. Okay, so straightforward from this to this, just referring to table. Then we already know that Hz is YZ over XZ. So this is actually, you need to multiply by to the XZ, and this one multiply to the YZ. So do that again, multiply, expand, and then inverse Z transform. So YZ becomes YN, and this is, you have a Z to the power of minus 1, so your Y is actually delayed by 1. So YN minus 1. And this is XN. Finally, you have YN equals to XN plus 0.5 YN minus 1. Okay, so what is this? So this is difference equation. What is our coefficient A? So from this, what is our coefficient? Coefficient A? Coefficient A is just looking at the output sequence. Not only 1
and 0.5
and minus 0.5. Okay, so this is coefficient A. What is your coefficient B? So just look at the output sequence, which is this one. Sorry, input sequence. So we have only 1. So it is B. Okay. So actually what you do here is, of course, this is, we just do some maths here. So without any, why we do this and everything. So actually this is a process of designing a filter. But for now, we just learn on how to convert the things. So this is like we are learning the tools first. So not implementation, not application. Application is later when we do filtering. Okay, so why do you need this? Because if you want to implement this in our system, so we need to find the A and B. So you store this in your ROM. You will store this in your ROM. And then if you want to implement the filter, so you run this thing, the difference equation, right? And because this is a FIR, so what is the option? The option is only 1. So you should solve the difference equation. But if the system is FIR, so there is another option. So in implementing the system, so you can do convolution. Okay, you can do convolution, right? And convolution is actually one mathematical operation which can be optimized. So there's a lot of ways on how to optimize a convolution. Right, and we will see some of it. You will see some of it. So, okay, so those are the things. So those are the things. Let's see what else that we have. Example 4. I think this is the last example for system function. So find difference equation for Hn. So what we have is 1, 1, 1, 1, 1. So how many? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And clearly this is FIR because you can count the samples. So you have 10 samples. So how about this? So how many samples that we have for Hn? So this is actually infinity. It starts at n equals to 0, the un. It ends at n equals to infinity. Okay, at n equals to 0, so this is actually 0.5 to the power of 0, which is 1. At n equals to infinity, so this one becomes a 0.5 to the power of infinity, so which is very close to 0, right? Very close to 0. So it's not 0, but it's close to 0. Okay, because if it is a 0, then it means that we can count. We can count the sample. But because even after at infinity, the value is not 0. The value is very close to 0. Right? So that's why we have an infinity number of samples. We call it infinite impulse response. And this one, finite impulse response. How finite? 10 samples. Okay. So solution, because what we want to do is find difference equation. Find difference equation. Because this is an FIR system, convolution can be used to obtain the difference equations. Or we already know that for FIR, Hn is actually equals to B. So this is B. Okay. And when it is a FIR, the A is actually equals to 1. Okay, so we doesn't have this one, we doesn't have this one. So what we have is only Yn alone for FIR. Okay, so then we can do it very straightforward. Actually, this is the equation generally. That's the equation. So we can summarize it as this one. So this is just a H0 xn. So what is a H0? H0 is 1. Plus H1. So this is a H1. So this is a H2, H3 until H9. Okay. H9 is here. And replacing those value, everything is actually 1. Everything is 1. So what we have is just xn plus xn minus 1, and you continue until xn minus 9. So everything is multiplied by 1 because the Hn is 1. Okay, so those are actually the B. So what is this? So actually this is actually equals to B. What is the A? A is here. A equals to 1 because the output sequence only have 1. So the sequence of the difference equation is too long. Let's look at a different technique. Okay, so sometimes we can manipulate this because this is kind of a very long, and where, so if we count this, so how many units? So units 1, 2, 3, 4, 5, 6, 7, 8, 9 summation. Because in discrete system, in digital system, so this kind of number of summation, number of multiplication, how many memory that you need is very, very important, very crucial. Okay, so if you can optimize it so that it can use less operation, so it will be better. Your processing time will be faster. Okay, because everyone wants to have a very, very fast system. So that's how we need to optimize it. We need to optimize it. So one way of doing it is now rearrange the equation, do Z transform, and obtain the difference equation. So actually we can do this. We manipulate the equation. So look carefully. So this is actually 1, 1, 1, 1, 1, 1, 1. So this is actually UN minus UN minus 10. So how is that? This is UN from 0 and then 1 and then 2 up to, let's say we have up to 9 here. Continue until infinity. Okay, so what is this? So this is UN. And what is a UN minus 10? So UN minus 10 is, so you have from 0 and then 1 and then 2 up to a 9, and then you have a 10. So you will start at 10 until infinity. So what are these values from 0 up to 9? Everything is 0. So 0, 0, 0, 0, 0, 0, and then you have your first value of 1 at sample number 10. Okay. And when you do this, this one, UN, minus this one, so what's left is this thing. Okay. So we can manipulate the equation into this in terms of UN, in terms of UN. So because actually any signal, any HN, actually it can be written in impulse unit, impulse signal or step signal. So this is actually using step signal, UN minus 10. And from our table, so we already know that our table, we have a UN. So it doesn't have to do a lot of calculation here, a lot of maths equation manipulation. So we just refer to this table. So that's what is a UN? UN is a 1 divided by 1 minus z to the power of minus 1. Okay, straightforward, we get that. So this is the first term, 1 minus 1 minus 1 divides 1 minus z to the power of minus 1. Okay, minus, so what is the difference on this one? So this is actually just UN, the same UN, but delay by 10. So when you delay by 10, so you have this additional term. How many delay? Delay by 10. So this is multiplied by z to the power of minus 10. Okay, so this is actually from, also from our table. Time shifting. Okay, so whenever you have a delay, so you need to multiply by z to the power of minus of that delay. So then we have this, we need to combine this. So this is the same thing, 1 minus z, 1 minus z. So this is actually 1 minus z to the power of minus 10 over 1 minus z to the power of minus 1. So we get this one. And this is in the form that we want. What is this? So this is our hz. What is the hz? Hz is system function, right? So this is system function. So then we know that hz is equals to yz divided by xz. So and then bring that up, those two. So this one bring up, so this one bring up. So then you have your yn minus 1 equals to xn minus 10. Or a more typical way of writing it. So yn equals to xn minus 10 plus yn minus 1. So compared to the previous, so what we need is actually a 9 summation. And then this one, 1, 2, 3, 4, 5, 6, 7, 8, 9 summation. And then you need a RAM, a memory to place this thing, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you need a 10 memory, okay, to place this value. But comparing this, so you just need 1, 2 summation instead of 9. How many memory that you need? 1, 2, 3. Okay, so this is where we can manipulate the equation, use a Z transform, do the forwards, do the inverse, so that we can. This is one way of how we can optimize our system. It is the same thing. So this is exactly the same. Yn equals to xn minus 10 plus yn minus 1. This is exactly the same with this one. So it produces the same outputs, but it looks different. It looks different. Okay, and actually we have seen this thing. I mean, a different form of solution from our quick quiz, right? From our quick quiz. So at least there are 3 form of solution. So we can do that. Okay, so it's quite flexible. So it's just that, so even actually until today, people are doing research on how to optimize things. Okay, so 11:55. Okay. I think we stop here for our first session, and we will start again at 12:05. Okay, so we will continue this story. So why we need to do this? Why we need to count all these things? So how it is done? So because it is very important for our implementation in a digital system. Okay, so that's all for now. So see you guys back at 12:05.
Okay,